for a couple of logistical things, and then we'll start the warm-up problem and let you know what's going on. First of all, happy National Oatmeal Day. It's kind of nice that the snow fell on National Oatmeal Day. I feel like that's kind of like a sign of the things that are to come, whatever that is, for better or worse. I hope it doesn't start snowing. That's like that book. You know what I'm saying?
Snow.
Yeah. Yes, thank you.
I love you.
I feel like he was making fun of me, but you understood what I was saying. Yeah. All right. Okay. So, just a couple of things about logistics for today and what's going on. We are not doing an assessment today, and I know that you were told that yesterday, and I apologize if that confused you. In fact, up until I woke up this morning, we were planning on it, but I felt like we were not quite ready for that. So, just so you know kind of what's going on, today my plan, please be quiet. Okay, my patience is not high today. We're going to start with a warm-up problem. I want to talk about the vector check-in sheet that you did, I don't know, like a week ago now, but I have not gotten back to you because it's been sitting in my backpack. I apologize. And then we're going to do some projectile motion practice. So we're going to talk through the lab that you did on Friday or Monday, okay? We'll work on some of the worksheet problems if we have time. And then if we still have yet more time, then we will do some extra practice. Why are we doing all of this? Because tomorrow there will be a check-in. Okay, that will be graded, and I want to make sure that you're feeling good about it. Okay, so we're going to do a bunch today. That's my focus for the day today. We'll do a little bit tomorrow as well to solidify things, to answer questions, whatever we need to do. Friends, I really hope you're listening because this is important stuff. Okay, and then we'll take that assessment. Thursday is going to be a little bit more review, and then Friday we are testing over all of Unit 2. Unit 2 involves 3 standards. The first one is horizontal projectile motion. The second one is vectors, vector addition and vector decomposition, or getting it into components. And then the third one is projectile motion at an angle, which is what we're going to focus on today. All right? So that's kind of what's coming up. I also want to let you know that the Unit 1 test retakes are available. I'm sorry it took me a little while to get those to you, but they are ready to go now. I would prefer that you get that done by Friday. If that does not work for you for whatever reason, I ask that you make sure to talk to me before Friday. If there isn't a plan in place, then we're not going to do it after Friday. Does that make sense? Okay? By Friday, or at least touch base with me by then. There are a lot of people that seem not to be paying attention, and I really hope that means that you don't need any of this information so that you don't have to ask me again. Because I get really, really frustrated when I say things over and over, and then I get the same questions. Okay? Please make sure that you ask questions as they come, but also please make sure that you listen. All right. Any questions as it relates to logistics? Okay. We are going to start with the warm-up problem. Here it is right here. So you're going to get your warm-up sheet out, write it down, write down your answer. Feel free to talk to one another. That's absolutely fine. But this is what you need to be focused on. Let's do it. Show me your boards, friends. All right, I'm going to write some things down. So hold them up so I can see them. Here we go. So I see ADCB. I see ADCB, ADCB, AD, and B equals. Okay, hold on. Stay right there. AD, B equals C. All the same. All zero. Did I get everybody? All the same, all the same. All right. So it looks, friends, like we've got 4 different answers here. I need somebody to advocate. Tell me why you say what you're saying. Help me out. Hopefully one of those answers is right. Maybe not. I don't know. You wrote something down on your board on purpose, right? Right? Like it wasn't just like some sort of, I don't know, magical pen thing. I'm talking about the X and Y. Yeah. It just says rank the acceleration. So I think that means the overall acceleration. So can you tell me what you're thinking?
Well, we said the same because like once it reaches its highest point, like starts falling back down, you know, and like the negative one because gravity.
Okay, so I think, can I interpret what you're saying? So it's going to go up and come back down, right? Is that what you're saying?
Yeah.
And so when the cannonball is right here, so tell me more about what you were saying.
Like In the y direction, it's going to be negative 9.8 meters per second because gravity pushing it down.
So the acceleration in the y direction is negative 9.8 meters per second squared. Okay. Is there acceleration in the x direction?
No. There's no parachute or no jetpack.
No parachute, no jetpack, no air. So there's no acceleration. So a sub x equals 0. And so Haley, make sure that I'm understanding what you're saying. You're saying that it doesn't matter how fast it's going, the acceleration is always going to be that? Does that kind of make sense? So if that's the case, if the acceleration, or excuse me, if the velocity doesn't matter, then what do you guys think? What based on that reasoning, which I think is sound good physics reasoning, what do you think the right answer should be here then? All the same, and I hear one say all 0. Why all 0? Why all the same?
I said all 0 because at the highest point, it's like it's not doing anything. It's not accelerating.
Is it accelerating at all
Yes.
in the y direction?
Yeah, I think.
So let's watch the frog, right? So we can make the frog go up and down. We can also just throw the frog directly up in the air. At the very top, what's his velocity? 0. What's the acceleration of the frog at the very top? What is it, Jordan? How do you know? Because I've said it like a million times. Is that, yeah? So it stops for just a moment, but the key there is the just a moment, right? Which means that right before it stops, it's moving. And right after it stops, it's moving, which means that its velocity is changing the whole time. Is that okay? So at the very top, even though the velocity at the very top is 0, its acceleration isn't 0. If its acceleration was 0 at the very top, that means that it would stay there. So let's watch it one more time. This is a big idea that a lot of people have a misconception about, which is why we talk about it forever, right? I've been saying this for how many weeks, how many months? I don't know. At the very top, does he sit up there for a long time? No, because his velocity changes, it slows down, and then it stops, and then it starts speeding up in the negative direction. So his acceleration is negative 9.8 the whole time. The whole time. Okay? So I think the answer should be all the same. Quick question for you. What if I changed their highest point to be just after launch? Would that change the answer?
Because there's no acceleration in the x direction.
There's no acceleration in the x direction. Is there acceleration in the y direction? Yeah. How big is it? Negative 9.8. Hey, I have a question. What if I did it again? And I changed this from just after launch to just before it hit. How would the answer change? All the same still. All the same the whole time because, friends, the acceleration in the x and in the y do not change at all. They are constant the whole darn time. The acceleration in the x is always 0. The acceleration in the y is always 0. Okay? If you're filling out that chart, right, the warm-up chart, there's that little thing that says takeaway. Do you know what you should write in there? What are some things that you could write in there? The acceleration is always constant. The acceleration in the y direction is always negative 9.8 all the time. The acceleration in the x direction, assuming there's no jetpack, assuming there's no parachute, and assuming there's no wind, right, or no air, is always 0. All the same. All the time. Always. I have one more question to ask you before we move on. I'm going to go back to the highest point question that we had at the beginning. I'm going to change a different word. Okay? I'm going to change the word acceleration to the word velocity. Rank the velocity of the cannonball when they each reach their highest point. I'm going to give you just a moment to talk with your table mates. I'm going to give you a moment to write down an answer on your board. I do want to point out to you that they all are launched at an angle of 35 degrees. Okay? I'll give you just a moment to give that a shot. But get the joke? A shot like a cannonball? All right, friends. Show me what you've got. So again, we're doing velocity here. I see AD. What did you have? A is greater than D is greater than B is equal to C. AD CB. Does yours matches this one, right? Is that right, Josh?
Yeah.
Okay, good. I just want to make sure. All zero, all zero, all zero. Do I have any other answers? All right. So again, all of these cannons are aimed at 35-degree angles. Rank the velocity of the cannonball when it reaches its highest point. Make an argument for me. One of these three answers might be right. Go.
At the highest point, it has that momentary stop where its velocity equals 0.
Okay, so I'm going to draw this picture again. And so, Ad, you're saying that here's the cannonball, and at the very top moment, its velocity is 0. It stops. Okay, so we're going to watch it and see. You ready? I'm just going to throw it towards you. Everybody watch at the very top of the curve. Here it comes. At the very top, does it stop? Does it stop in one of the directions? Which direction does it stop in? The Y? One more time. Let's do it again. Whoa!
Sorry.
That's okay. It's like, whoa! It's like, gotta get in position. All right. In the Y direction, it for sure stops. But in the X direction, does it stop? No, and you have to be careful because the way the question is worded, right? I want to know the total velocity. So at the very top, in the Y direction, it definitely stopped because I could draw my Y velocity goes like this, and then it goes like this, and then at the top it's 0, and then here it's going down, and here it's going down like that. Yep. But talk to me about the X direction.
It stays the same.
It stays the same because the acceleration is
0.
0. Hot diggity. So that means that whatever the velocity is at the beginning, it's the same, right? So it's going to be this fast, and then it's going to be this fast, and I'm trying to draw all these arrows the same length. I didn't have my ruler out, though, so forgive me if it's not perfect. You get the idea, right? They're pretty darn close. Okay? So I see what you're saying in that the Y direction is 0. But does it make sense that the velocity is not quite 0 there? So which of these then, how do we determine? What'd you say? Their initial velocity. So, but the velocity here is just the what part of the velocity?
X.
Just the X piece. But, question, if this is 35 degrees at all of these, 35, etc., does it make sense that the X part here is going to be 80 meters per second times the cosine of 35? You with me there? This one's going to be 40 cosine 35, 40 cosine 35, and 60 cosine 35. Cosine 35 is the same in all of these cases, isn't it? So the bigger the initial velocity, the bigger the initial velocity in the X direction. So I think then that 80 is biggest, and then the 60, and then B and C should be the same. Yeah, so I'm thinking this is the right one. Yeah. There's a lot of physics thinking that goes into that, right? Okay. It's good thinking, good stuff. Questions that we have right now. We good? Everybody happy? Yay! You might want to write down a little something in your warm-up problem sheet about that too. Just to remember, right, that the velocity isn't 0 at the top. The velocity is only in the X direction at the top. That's another good little takeaway thing to keep in mind. Okay? All right, so on your lab that you worked on either on Friday or yesterday, depending on which day you were labbing, part A, so everybody should have this yellow piece of paper out, okay, because we're going to go through this today. Your homework for tonight is to get this done if you don't have it done. So I'm going to help you with this now, so don't assume that you can figure it out. Like, I want you to do it now with me right now, okay? So in part A, this was part A, you measured your displacement in the Y direction in meters. So your launcher looked something like this, okay? And here it was like on its stand, and here's the table, okay? And then the projectile came out here and went boom, like this, okay? So the y direction, the stuff you measured in the y is right here. That's delta y. That should be measured in meters, okay? And you should have put that value here, okay? So I'm not going to grade on an exam. I'm not going to ask you to do conversions, but that doesn't mean it's not important, right? So if you measured that that was like 25 centimeters, how many meters is that? What'd you say, Cole? 0.25. I'm not saying that's the right answer. I'm just telling you that's how one would do the conversion, okay? And then you measured this x value, delta x, also measured in meters, and that value should go here. This right here is just practice of standard 2.1, okay? This is standard 2.1, which is the horizontal launch standard. So we can set up our givens chart just like we always do. Delta x, VIX, AX. Got delta y, VIY, AY. And the thing that pulls it all together is time. Okay? You know your delta y. You know the initial velocity in the y direction, that's 0. You know the acceleration is negative 9.8. Okay? And you can use all of that stuff to solve for time. That's the first thing that it asks you to do, is to calculate the time of flight. Use that time, the initial velocity, or excuse me, the distance in the x, the range, to solve for VIY. Okay? That's the goal of this. This initial velocity that you calculate in part A, you will use in part B. You have to know this. This is the launch speed of the launcher, regardless of if it's launching horizontally or launching at an angle. So this value right here, this one right here, is the initial velocity for part B as well. Okay? So on the back for part B, I'm going to go ahead and draw this right here just so that you can kind of see how it looks. The initial velocity here, VI, is the value calculated in part A. All right? So if you don't do part A, you can't do part B. The value you calculate in part A is the initial velocity here. Then, this is standard 2.3. This is the standard where we're breaking things down into pieces. So we're going to take that VI and we're going to break it down into an X part, VI in the X, and a Y part, VI in the Y direction, given the angle that you measured. So you've got an angle here, measured in degrees. Your height should be the same for all of your launches. And then your initial your range, you're going to use to do your calculations. Okay? I'm going to go down for just a moment. This process here is the same as what I showed you on that video that you watched the day that you weren't doing the lab. And this is just using sine and cosine, sine for the VIY and cosine for the VIX, to break that initial velocity into pieces in the X and the Y direction. Okay? So you took data for 4 angles, but the only thing I'm asking you to do is calculations for 2 of the angles. Friends, all this is just an opportunity to do calculations. Okay? I could have you do it for all 4, but it doesn't really matter. So we're just doing it for 2 just so you can get that experience. So you're going to use vectors to determine the initial velocity in the X and in the Y. That's what we just talked about. And that is given right here for you. Okay? In the X and in the Y. Okay? Some people asked last period what that star is. It's really just a multiplication. I apologize if that confused you. Just a multiplication sign. VI times the cosine of theta, then VI times the sine of theta. Same thing here. Okay? So that's just breaking it down. So you're going to fill in your angle. So maybe you do 45 degrees. Everybody did 45 degrees. Okay. You're going to put in your value for X. Keep my colors consistent here. It was purple. You're going to fill in your value for X, the measured value that you got in this column right here. You're going to calculate your Vx. You know the acceleration. And using the X stuff, you're going to solve for time. Okay, so how do we do that? Well, we're going to do delta X is equal to Vix times t plus 1/2 ax t squared. There's nothing magical about this, okay? This is really just a hands-on problem that's exactly like the problems on the purple sheet. It's the same thing. The acceleration goes to 0, and you can solve for time. Time is equal to delta x over vi in the x direction. Remember that Vix is just going to be the vi that you found in part A times the cosine of the angle that you found, or that you measured. So that's the first stuff. That's part 2. That's step 2 up here. It says based on your measured range, use the x stuff to calculate the time. And then you're going to use the y stuff to calculate the height. So we're going to calculate this value. And you should get something close to the value you measured. Okay, that's what we're keeping our fingers crossed for. You're going to calculate this using delta y is equal to VIY times time plus 1/2 AY t squared. So you know your time because you found it in the other part. You know your acceleration. You calculated this. So you're looking for delta y, and we're going to compare that to the value that you measured. Okay? That's what I'm asking you to do. So you can pretend like you don't know delta y, and hopefully you get something close to 0.25 or 0.26 or whatever your height was. Okay? That's what we're hoping for if your physics is consistent. Okay? So if that doesn't make sense to you, or if you need more help with this, that's 100% fine. You can watch this video again because I've been recording this whole thing, okay? Or you can come in and hang out with me and we can go through it. I'm very, very happy to do that with you. But what I would like is for you to finish this process before tomorrow. I'm going to give you just the last couple minutes before the bell rings to do that. The other thing that I'd like for you to finish before tomorrow, if you haven't yet, is these problems right here on that purple sheet, okay? That's what you are responsible for before tomorrow, okay? Do not put your stuff away. You've got another 3 minutes. Use those 3 minutes to get started so that you have a jumping off point when you start your homework, whenever it is that you do that. All right?